Okay, section 3.7. This is example 4. And again, I like this example because it needs extra variables. So they say we have, and also so it needs extra variables and it's constrained. And so that's how we're able to solve it in this class. So we have two posts. One's 12 feet high, one's 28. So there are my two posts. I know that's 12, that's 28. And they stand 30 feet apart. Okay, so we know that that distance is 30. And we're going to attach two wires to a single stake. Okay. And it says where should we put the stake? So here's the stake. Where should we put that to use the least amount of wire? Okay. And so what they do is they suggest that, hey, we just call, say, that distance x, and if that's x, then that distance is 30 minus x, and let's just call that distance there y and that z. Now, why the y and z? Well, because the total amount of wire, all right, we want to minimize wire length, and that wire length is just y plus z. Okay, so again, there we're trying to minimize something of two variables, but we have constraints, right? We've constrained x, so this is subject to x has to be between 0 and 30. Okay, so that's one thing about x, but also x, assuming these poles are put straight up, x and y need to satisfy the Pythagorean theorem. And so we have that x squared plus 12 squared has to equal y squared. And we need that, then 30 minus x quantity squared plus 28 squared has to equal z squared. Now the question is, can we get away, like we did in example 2, with just using the squares? And I don't think so. Because what I'd like to do is just substitute in here what we have, but I just I don't think that's going to work, because you might say, oh, we'll just make it y squared plus z squared, but that's not the same as the quantity y plus z squared. And so if we want to minimize this length, I don't think we can just make it, let's minimize y squared plus z squared instead of y plus z. Okay. I say I don't think. I'm pretty sure we can't, but right off the top of my head, given that we know those y and z would also be greater than 0, off the top of my head, I don't know that I have a particular example where I could say, oh yeah, see, that doesn't work. Okay, and so we're just going to have to take the darn square roots. So y is equal to the square root of x squared plus 144, and z is equal to the square root of 30 minus x squared plus whatever 28 squared is. Okay, and so what we want to do is minimize that sum. So we want to minimize the square root of x squared plus 144 plus the square root of 30 minus x squared plus 28 squared, and that is still subject to ST. I'll use for subject to 0 is less than or equal to x is less than or equal to 30. So this is a section 3.1 problem. I guess that was 3.1. You know, a continuous function on a closed interval, and so we could use those techniques. But in the end, you know, we need to take derivatives, set them equal to 0, and that's just sounding nasty, nasty, right? And so I think at this point, I'm going to turn to Sage to do some calculations. Okay, so if we, I don't know, if we call this W, I want W prime of x equals. Okay, so let's try to figure out what that is. So I'll go here. This is what I use for example 2, and I'll need to keep x. Now, you know, what I could do here is I could define our relationships though. So I've got y, and that is the square root of, and that was x squared plus 144. Or I could even, just to make sure I didn't screw that up, I could say 12 squared. And my z, so I'm just editing this. Part of the reason is I'm showing you, this is a nice way to do things actually. Take stuff you've already done and you know, put it in here. So this is 30 minus x squared, like that. No, sorry, 30 minus x and squared, and then plus the 28 squared, and put that in parentheses. And then my function, I guess I'll I don't have this function anymore, so I'm just getting that out of there. And instead of d, I'm going to call it w. I could leave it as d, but you know, I'm going to, because it is distance of wire after all. But I'll call it w, since that's what I called it in the beginning here. So this is w, and that is just the y plus the z. And now I could change my comment, you know, define our, not distance squared, but, you know, and I could say even here wire distance, not define our point, but I define define separate wires. All right, I did that. And then I'll show our objective function, and then I will take its derivative. So I'll do that. so that doesn't change, and I'll look at that, and I'll still want to solve that, so I'll still call it S, and W P equals 0. So set, and here I'll change that to a W, and I'd still like to just take the second derivative. I might as well. Now it's on a closed interval. I don't really have to. I can just take the critical points and solve that, but why not take the second derivative? Now all this stuff, I'm gonna put comments on it for a moment because it will just give me errors anyway. So I'll make all those comments just for a second while I go through and try this. Okay, so far so good. That looks good. There's my derivative, and there's the solution. That's nice, only one critical number. And there's my second derivative. And so, yeah, only one critical number. And, oh, x equal, oh, wow, I just noticed. Look at this. It didn't come up with the answer. Bummer. Right? You know, so this is great, you say. What do you mean it's great? No, really, it's great. Because you see the limitations of the technology, and that, you know, given I see an x here, you know, it's solved for x, but no, it didn't solve for x. Now, there are things I might be able to do, maybe, to try to get this to work. Now the book actually shows some algebra to do it, and so the book is pointing out you can do this, right? You know, you and I can solve this, and but certainly just throwing it into our technology didn't make it happen. So unfortunately, we were not able to find a critical number this way easily. Now, again, we could make this all happen, and eventually we could get Sage to solve this. But oh, we've got another technology, and notice, you know, I can go to it, but now I have a reason to tell you I'm going to Desmos, right? I'm not just going to Desmos immediately and saying, oh, I'm just going to graph the function and, you know, all that kind of stuff. No, I'm trying to do it by following the steps, and well, I got stuck here with solving for x. And realistically, what I like here is that no, we can do it. It is a book problem. They show us the algebraic steps to get it an answer, but it could be that wouldn't work anyway, and so we're stuck here. And so what I want to do is go to Desmos and put this function in. So now I could try it. I could try some things to enter it quicker. This square root one doesn't look so bad, but the z part looks kind of nasty to put in. I'm going to try highlighting it, doing a Control-C, going to Desmos, and saying, okay, I might as well leave it as f of x, and I'm going to do Control-V, and it didn't know what the square root was, but other than that, it did fine. So I back it up, and I say SQRT. There made the square root. Now I'm going to highlight this stuff do a Control X and place it in there. So yeah, that wasn't so bad. Now I'll get out of here and delete those two things. So f of x is that plus, and then the other one was the square root of x squared plus 12 squared. Okay, and I can grab this thing and kind of pull it wider so I can see that whole function. Now, I don't need that point. I have the function here. I don't need all that stuff. So I'll just get rid of all those things. So there I've got the function. I don't see it. I'll have to zoom out here a little bit. There it is. Okay, now also here's an interesting thing, all right? I can very quickly go here and see the minimum is at x equals 9. How about that? So we would want that 9 feet from the end. But we can take derivatives and so forth. But let's take this opportunity to also look at g of x equals, and now let's look at what would have happened had we just taken that, so Control C, Control V, and then plus the inside of this one. Okay, that would have been our y squared plus z squared. Okay, now that's a much bigger function, so I'd have to zoom out, right, because I took square roots, so I can't really see the function. It's going to be pretty big by the time I get here, but I can still plot g prime of x and look for where g prime of x is 0. It's 0 at 15, not the same place. Okay, because if I look at f prime of 0, its critical number, or f prime of x, sorry, and look at where it's 0, right? It's 0 at 9. So, yep, this would have given us a bad answer had we done y squared plus z squared. So we'll get that out of there. But there's our f prime. We can see it's 0 at 9. And so I can kind of combine these two things, right? I can go here to Sage and I can tell you there's the function I need to minimize. There is its derivative. And here is its second derivative. I could write that down for somebody. And back here, well, either place, you know, I can also do a numerical second derivative, f double prime of x. So there's the second derivative, and I can check. Now, you know, here I can obviously see everything's concave up and all that, but here I can do f double prime of 9 and get 0.069. It's positive, and so I can do it that way. I can also evaluate at 0 and 30, f of 0, f of 30, and f of 9. And we see that, you know, that's 53, that's 60, that's 50. And so if we come back to combining our written stuff with what we got between Sage and Desmos, yeah, we can write down some nice things. Okay, so I'm going to come back here to Sage for a minute just to look at this, and then pull up our W prime. And so here's our W prime. So the x minus 30 over that square root thing, and then just x over that square root thing. So I think I can remember that to write that down for my derivative. And so I'll go back here, and okay, my derivative is, oh, now I don't remember, was it x squared or something? See, my memory is not so good. X minus 30. Okay, so now I've got it. Mind like a steel trap. X minus 30 over the square root of our 30 minus x, quantity squared, plus 28 squared, and then plus x over the square root of x squared plus 12 squared, or 144. Okay, so there's my w prime, and I can say here, by Sage. Okay, so I've got that. W prime of x equals 0. X equals 9 by Desmos. Okay, and I've got that, and I could include the picture. You've seen the picture, and then I could do W of 0 equals 53 point something or other. W of 9 equals 50, and W of 30 equals, what was that, 60 point something or other. Go back and look at Desmos here. Yeah, 60.3 and 53.06 and 50. Okay, go back to here. Okay, and again, by Desmos. And so since we had a continuous function on a closed interval, I can look at this and say W of 9 equals 50 is the minimum. Okay, so I can use that, and the other possibility would be to look at W double prime of x, and I could write that down, but actually all I really care about is its sign. And so the question is, here I did f double prime, and let's turn off f prime, and I can zoom in a little bit, and what I see is it appears, so the best I can tell on the interval here between 0 and 30, is I just kind of scroll back and forth, I can actually write is greater than 0 for 0 less than or equal to x less than or equal to 30. Okay, that's greater than 0 by Desmos. Okay, so it's concave up. All right, so concave up means we have our minimum at 9 and 50. Okay, so I use both Desmos and Sage. If the second derivative had been a little nicer looking, I probably would have written that down and mentioned Sage. Oh, I didn't come back here when I finished writing here. So I said W double prime of x is greater than 0 for x greater than x between 0 and 30, and that was by Desmos. So I see that it's concave up, and I can circle back and talk about so 950 is the min. Okay, that's the point at which the minimum happens. Okay, so there we go, and that is example 4.